Welcome to our lecture on exact sampling distributions. Imagine you are sorting apples at a farm. If you know exactly how the apples grow, you can predict the weight of any small basket with absolute certainty. But with random apples, you would need a massive truckload to guess the average. In statistics, exact sampling distributions are like knowing those exact farm rules. They give us perfect mathematical formulas for how sample data behaves, no matter how small our sample is. Let us dive in and see how this works. Now that we understand the basic idea, let us look at what an exact sampling distribution actually is. In many real-world scenarios, collecting massive amounts of data is simply too expensive or impossible. An exact sampling distribution is a probability distribution derived purely mathematically, without relying on large sample approximations. However, this mathematical perfection comes with a strict requirement. The entire population from which we draw our sample must follow a normal distribution, meaning it must look like a perfectly symmetrical bell curve. When this assumption is met, we can make perfectly accurate predictions, even if we only have 5 or 10 observations. This strict requirement leads us to our first key mathematical model. Here we have the formula for the standard normal variable, denoted by Z. Conceptually, this formula tells us exactly how far our sample mean is from the true population mean, measured in units of standard error. Let us break down the symbols. Z is the standard normal variable. X bar represents the sample mean. The Greek letter mu is the true population mean. The Greek letter sigma is the population standard deviation, and n is our sample size. Notice the denominator. As the sample size n increases, the standard error shrinks, which makes the overall distribution much tighter and more precise. Beyond the mean, we also need to understand the spread of our data, which brings us to the chi-square statistic. This formula shows exactly how the variance of a small sample relates to the true underlying population variance. In this equation, the Greek letter chi squared represents the statistic itself. The variable n is our sample size, s squared is the sample variance, and sigma squared is the population variance. The units here are always the square of the original data units, like squared kilograms. If your sample variance perfectly matches the population variance, the entire value simplifies to n-1, which is a critical value we call the degrees of freedom. Before we move on, let us see this uncertainty with a concrete visual example. Look at the diagram on your screen. The solid blue line represents the true population distribution, which is a perfect, tall bell curve. Now look at the dashed red line. This represents the exact distribution for a small sample drawn from that same population. Because our sample is small, we have more uncertainty. This extra uncertainty flattens the curve, making it wider and giving it thicker tails. The exact distribution perfectly models this extra uncertainty, so we do not make false conclusions when analyzing limited data. Seeing that wider curve brings us to an important practical problem. In the real world, we almost never know the true population standard deviation sigma. Because it is unknown, we are forced to estimate it using the standard deviation of our small sample, denoted by S. Guessing the standard deviation from just a handful of observations introduces even more uncertainty into our math. The standard normal distribution can no longer handle this extra guesswork perfectly. We need a different exact distribution that mathematically accounts for this specific type of uncertainty when dealing with small samples from normal populations. To handle this extra uncertainty, the mathematical model shifts from a normal distribution to a student's t-distribution. Conceptually, this formula is almost identical to the Z formula we saw earlier, but with one critical difference. Instead of the known population standard deviation sigma, we substitute it with S, the sample standard deviation. The variable t represents the student's t statistic. X bar is still the sample mean, mu is the population mean, and n is the sample size.
By using S instead of sigma, the t-distribution mathematically adjusts for the extra doubt introduced by our small sample size.
Now that we have our formulas, let us see this with a concrete example. A quality control engineer is testing the battery life of 12 smartphones. We are given that the battery lives follow a normal distribution, which is the core requirement for exact distributions. The engineer wants to test a claim about the average battery life. But there is a catch. The true population standard deviation is completely unknown. Our goal is to determine which exact sampling distribution the engineer should use to analyze this data and why that specific choice is mathematically correct. Continuing with our engineer's problem, we need to evaluate the conditions given to choose the right tool. First, we look at the sample size. The engineer only tested 12 smartphones, so n equals 12. In statistics, any sample size strictly less than 30 is firmly in the territory of small samples. Because the sample is so small, standard large sample approximations will completely fail here. They would give us inaccurate probabilities. Therefore, we are absolutely required to use exact sampling distributions to ensure our mathematical conclusions about the battery life are valid. This brings us to the final step of our example. We know the population is normal and the sample is small, but the true population standard deviation is unknown. Because it is unknown, we must estimate it using the sample standard deviation, S. As we learned earlier, substituting S for sigma changes the math. Therefore, the final answer is that the engineer must use the exact student's t-distribution. It is the only mathematically correct model for this specific scenario because it perfectly accounts for the extra uncertainty of guessing the standard deviation from just 12 phones. So, we have successfully applied the t-distribution. But this leads us to an important question. What happens if the real world is not perfectly normal? This introduces the concept of robustness. A statistical test is called robust if it still gives accurate results even when its underlying assumptions are slightly broken. Fortunately, the t-test is quite robust to non-normality as long as your sample size is at least 15. However, if your data exhibits extreme skewness, meaning it is heavily lopsided with a long tail to one side, the robustness rule completely fails. The exact distributions will give inaccurate probabilities. When extreme skewness breaks our exact distributions, we must fix the data's shape before doing anything else. We do this using a mathematical transformation, such as the logarithmic transformation shown here. Conceptually, taking the natural logarithm pulls in extremely large, lopsided values, forcing the data into a more symmetrical, bell-like shape. In this formula, y represents the new transformed data point. X represents the original skewed data point, and ln denotes the natural logarithm. By applying this formula to every data point, we can rescue our dataset and make it safe to use with exact sampling distributions. Let us see how this transformation works in practice with another example. A biologist is studying the reaction times of a rare insect and collects a sample of 18 insects. The data shows extreme right skewness, meaning most insects react very fast, but a few are extremely slow. The biologist wants to use a t-test to find the average reaction time. We need to figure out how she should proceed to ensure her mathematical analysis is valid, given the severe deformity in her data. Continuing with the biologist's data, we must first check the robustness conditions. Her sample size is 18. Since 18 is greater than 15, the t-test would normally be robust enough to handle a slightly imperfect bell curve. However, the problem explicitly states that the data has extreme skewness. This extreme skewness is a critical roadblock. It completely destroys the mathematical foundation of the exact distribution.
Because of this severe deformity, the biologist absolutely cannot use the exact t distribution on the raw original data.
To solve this problem and reach our final answer, the biologist must fix the extreme skewness. She does this by applying a logarithmic transformation to her data. By calculating y equals the natural log of x for every insect's reaction time, she pulls in those extremely slow times. This mathematical adjustment makes the lopsided curve look much more like a symmetric bell curve. Once the transformed data looks roughly normal, she can safely and accurately apply the exact student's t distribution to her sample to find the average reaction time.
Now that we have seen how to handle different scenarios, let us zoom out and understand why this matters. Exact sampling distributions are the absolute backbone of modern scientific research, medicine, and engineering. In the real world, testing thousands of subjects is often impossible. A medical trial might only have 10 patients with a rare disease. An engineer might only have the budget to crash test 4 cars. Without exact distributions, we would have no mathematical way to draw valid, trustworthy conclusions from these small, expensive samples. They ensure that a new drug is effective or a bridge is safe.
We have covered a lot of ground today, so let us review the key takeaways. First, exact sampling distributions provide perfect mathematical models for small samples without relying on rough approximations. Second, they require the underlying population to be normally distributed, utilizing tools like the T, F, and chi-square distributions. Finally, while tests like the t-test are robust to minor deviations, extreme skewness always requires a mathematical transformation before these exact tools can be safely applied. Understanding these rules ensures your statistical conclusions remain perfectly valid, even with very little data. Thank you for watching.